In today's tech talk, we'll be looking at in Elsevier how we are empowering clinicians, students, researchers, every week, every month, every quarter, so on and so forth. So I've taken a couple of examples from our offerings like Clinical Key, Science Direct. These are enterprise search engines which enable particular set of users to search and retrieve relevant content that is required for their knowledge building or enhancing activities. Not working. Just to have some background about how they are built. Crawling and indexing. Okay. 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 Anything else? Any other answers? Okay. Okay. So going back to the previous example that I've taken, like generic search engines and enterprise search engines, do you see any difference in the way the search engines are built? Or is it same irrespective of the category? Context. Okay. Okay, that's a good one. Okay, enterprise, the content is proprietary. Yeah. In terms of the search functionality, do you see anything else? I mean, say any specific. Okay. 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 Tagging might be better. Okay. Okay. Mm-hmm. Mm-hmm. Okay. These are all good ones. So for enterprise, because the content is proprietary, probably the focus would be trying to cater to the specific needs of end users, specific set of users. So the queries are much focused and they try to incorporate a lot of semantic meaning into the query and try to extract all content that is relevant to the search string. Not only a basic string based search, but also we take into the context and semantics into consideration and try to retrieve all results that are related to the query that is being searched for. So since we are talking about clinicians, nurses, and students, so we need to be very particular about what these people do at the care teams. Basically, these people belong to the care teams. So at the point of care, they need to take decisions on a faster basis to actually give proper treatment and advise better medications to the patient so that they get quick treatment and get discharged very fastly without being suggested unnecessary tests or I mean say additional cost for medication and all those things. So these care teams, they have a lot of complexities and challenges on a day-to-day basis. So as all of us know that there is an ever increasing complexity of diseases. So there are even though there is a set of diseases that people know about it, there are so many comorbid conditions, so many rare diseases, combinations. So it becomes very difficult for a care team to actually diagnose what's happening with the patient and to suggest a proper medication. So balancing efficiency and consistency across the care continuum. This is again another challenge. So basically every doctor will have his own way of treating a patient. So if there is a standard way of treating the patients and suggesting either laboratory examinations, diagnostic examinations or medications, so everybody knows what's actually happening. So if you get a treatment in one hospital and if you want to go to another hospital, if there is a standard way of treating a patient, then they know that okay, this was done, it didn't work, probably this should be the next option that is in front of us. That's not valid as of today. Every doctor has his or her own way of actually treating a patient. Okay? And they have a lot of difficulty keeping up with clinical and patient trends. These keep changing a lot. There are a lot of clinical trials happening on a regular basis. Some medications which are valid till now are become invalid in future. Okay, there are new guidelines that are being published. which tells like what would be the best practice for treating a particular disease. Okay, so they need to keep up to date with all of these things, and how they can actually address all of these complexities and challenges. So they need like a set of tools which are reliable, okay, and can give evidence-based information to them so that they can make better informed decisions. That's like what most of the K team people will look at. So not only getting like access to the evidence-based information, but they should be able to get this information very fastly. So if they want to look at like a particular guideline for treating a disease, they have to search through Google or any other website and spend hours of time together to find out like what's the relevant guideline that he or she is supposed to use for treating a patient. Then it's a lot of waste of their time, and they cannot afford to waste that much amount of time. They must be able to deep dive into the latest evidence and research so that they can take like better decisions. So there are cases, I have told you, like say if they are searching something in Google, probably if they end up seeing like 10,000 results and going through every result and figuring it out like which one is relevant and which part of the research publication of the document is relevant for their particular scenario, it becomes difficult for them. If there is an easy way to navigate, then the life of the care team will become very easy. They should have a simple single source way of accessing all of this information from anywhere, basically, from any device. So we at Elsevier are passionate about health because like we publish a lot of medical content, and we have a lot of, Bible medical books which are widely used by medical students throughout the globe. Okay, so we have very rich source of medical content with us. So we are obviously passionate about health. Okay, so we are trying to provide like unique experience for student researchers and clinicians by providing various kind of offerings which will enable them to take better decisions. So I've listed a couple of offerings, especially for clinical key, when we do have a lot more other offerings for different areas. So clinical key is specifically for clinicians. Okay, so it's a clinical search engine which thinks and works like a clinician does, basically. Probably I'll quickly try to go to the next one, like clinical key nursing. So this is a specific tool which will equip nursing faculty and students to take better decisions in their nursing jobs. And there is a clinical key student, and this will equip the students to go through a set of question banks and prepare for their medical examination so that they can become masters in their particular chosen subject area. And depending upon the product, the end users are different and they have like specific needs. So we have tailored solutions for all of these needs, and the content that is used might be common. It might be overlapping across the products, and there are certain books and resources which are specific to certain kind of products. Okay. There is a quick video, probably I'll play this one.
With more specialists to coordinate, a higher volume of comorbidities to treat, and an increasing number of patients who want to share in decision-making, your clinician's world has never been more complex. As a result, 2 out of every 3 patient interactions generate questions in clinicians' minds, and they're only getting harder to solve. And 60% of those questions go unanswered because clinicians don't have time to find answers. They look but can't find them, or they don't trust the answers they do find. It's a problem that's not going away. In fact, it's estimated that medical information doubles every 73 days. Tools like YouTube, Google, and Wikipedia are typical destinations for clinical teams who need answers, but these sources can be inaccurate and inconsistent. Clinical teams often rely on summary content. However, complex cases demand more in-depth information, requiring clinicians to go deeper on a topic to accurately address the patient condition. For clinicians, this means using unproven or incomplete resources that waste crucial time for patient care. And for patients, it means unsatisfactory experiences, and worse, a greater risk to their health and safety. To better benefit patients and combat the complexity of today's healthcare landscape, you need resources you can trust to provide accurate, complete, and relevant information for your clinical practice. Finding accurate answers is just the first step. What you really need is alignment, so your clinical teams are working from the same evidence-based information, whether they are newly licensed or a seasoned specialist. This new perspective on information means more efficiency for your teams, who can now operate from the same trusted answers. Your organization can reduce your overall spend on clinical decision support, and most importantly, you can minimize the possibility of an error that could put patient outcomes at risk. This is why more and more health leaders are turning to Clinical Key to improve clinical practice through informed, confident decisions. Visit us online to learn more.
This is a short video which talks about like what are the difficulties and how we are trying to address those challenges and have consistent information shared across all the K team professionals. So since we are looking at like particular offerings of Elsevier like Clinical Key, this is like a screenshot of the UI, and clinicians can search for a particular term and they get to see like relevant results which talk about or give more information about the search query. So the search query here is asthma, and they get to see a lot of results. So here you see about 24,399 results. They are a lot, but they have a lot of filtering options, and based on their needs, they can apply the relevant filters and drill down to the set of documents that are relevant for them and look into only those documents that can give, say, authentic evidence-based information to make better decisions. And here you see like there are, we call these as POPs internally. So you see a button for summary, diagnosis, workup, and treatment. So if a particular clinician is looking at like treatment modalities for asthma, and if he believes like this is a right document, like asthma in adults is a right document for him to look at, and if he needs like specific information about treatment modalities, he can click on that particular option, and directly he will be taken to the respective part of, respective position in the actual document, so that without like he scrolling up and down, he goes to the relevant place quickly and can look at like whatever information is required. Also, there is an index towards the left-hand side, and it has a lot of other information, and based on the need, you can quickly navigate. This is like a screenshot for Clinical Key student. As I've told you, like say here, because the target audience are different, so we have different kind of options. So especially the question banks that you see on the top. So these are like a set of question banks that are available, which cover like a lot of information about all the subject areas where a student is preparing for, and they can take these mock examinations and prepare well for their national examination. And also they can have like a kind of a library wherein they can keep a track of all the books they are reading, and we have internal options to suggest like better books if a student is not performing well in a particular area. So we have a way of tracking them and suggest like relevant content so that they can read and prepare well for that particular areas. So not only English, like we also have offerings in other languages. So this is a screenshot for German language and a French Clinical Key. So we have, localized content for these offerings, which are specific to German, and there are certain books which are like globally valid. So we do a translation and make those books available on these offerings. So now let's look like what's happening behind the scene for building like a search engine like Clinical Key. So as we know, like this is an enterprise search engine. So we have a restricted corpus, and then we go into the other aspects like building an ontology, building an NER system, relation extraction, building a knowledge graph, indexing, and search. So here, all those trials. And we have information regarding drugs, drug class overviews, drug monographs, and there are a lot of guidelines which are like being used for indexing and making the data available to the users. We have information about patient education, multimedia, audio files, as well as like video. And there are some procedure videos which especially showcase like how a particular procedure is done in the operation theater and what needs to be done, say precautions, how a person has to prepare for doing this procedure, so on and so forth. Okay, and we also have clinical calculator and clinical focus content. So since I mentioned clinical calculator, I just wanted to show you one screenshot of a clinical calculator. So this is like a calculator for estimating peak expiration flow variability in asthma. So based upon like say the real-time values, a clinician can enter these values into the calculator and it will tell like what needs to be done in the next step. And there are various categories based upon like the disease. So they can select like appropriate calculator and look for like the next actions. Yeah. So since we have looked into the corpus, so because the search is pretty much focused, so we cannot simply build a search engine by creating like extracting n-grams from the text and building an inverted index. So that might result in like say some of the results, but not accurate semantic related information. So we build an ontology internally. We call it as Elsevier ontology. It's a multilingual ontology which is built currently in English, French, Spanish, German, Brazilian, Portuguese. And we are also expanding it to other regions like Nepalese, Arabic, Somalian, and few other languages. So here this ontology is a concept-based ontology. So all the terms, their synonyms, translations, everything is mapped to a particular unique ID called as IMUI. So irrespective of the language you are looking at, so every concept would have a unique ID. And it also provides a lot of semantic information between various concepts that are there in the ontology. So we also do an explicit mapping between standard international coding systems like ICD-10, ICD-9, SNOMED-CT, LONIC, RX norm, so on and so forth, so that like say irrespective of the content that we use for building the indexes, so we have a standard way of interpreting them and extract like say better relevant results. And this is continuously updated almost on a daily basis based on like say the new content that is coming into the system. We keep looking for like whether there is any new terminology or new terms that could be added to the taxonomy so that we are up to date with the content. And this is like heart of a knowledge graph that we are building internally, and that powers a lot of other applications within Elsevier. So here is a screenshot basically. So I think it's very difficult to read it, but you have like a medical name, synonyms, the mapping for various standard coding systems for a given term. So probably this would be a better slide. Yeah. So here you see like this is a medical name, which is, yeah, the consumer friendly name is a breast cancer, and there's a medical name. Most of the K teams would know this term using this name, malignant neoplasma of the breast. Okay. And there are a lot of synonyms for the same term. So it is a disease, and we have a semantic type, which is neoplasma process, and there are various mappings with international standards. And we also keep a track of what are the child elements for this term and also the parent elements. And we have like a lot of semantic relations extracted for every concept, like has a physician specialty, has cause, has clinical finding, has diagnostic procedure, has treatment procedure, has drug, has complexity. So these are very widely used semantic relations, and there are many more, close to 40 or 50 different kind of semantic relations. And again, depending upon the product offering and the need, we are trying to expand these semantic relations into various other categories, like pain severity. Somebody would like to know, like for a particular disease, whether it's like mild pain severity or very high or medium, and based on that, the treatment modality might be different. So we are also going into that detailed level of capturing the relation information. And here you can see a knowledge graph in a pictorial format. So this is a core concept, and these are all the other concepts that are related to the core concept, and you have different relations that are capturing or that link between like different concepts that are there here. And with this kind of knowledge graph, we can answer like a lot of queries like what clinical findings are associated with breast cancer. So you can pinpoint to a particular document and retrieve like relevant information much faster. And since we are talking about ontologies, and also as I've told you, like say we keep adding a lot of content not only in English but also in other languages. So we need to build like and keep the ontology up to date. So this is like one of the flows that we use internally to expand the ontology. Not only the flow, but one of the flows. Okay. So as I've told you, like say we keep getting a lot of content on a day-to-day basis. So we take the content, and based on the need, we try to identify like say the most relevant set of documents that needs to be used for mining and extracting relevant concepts that could be added back to the ontology. So for this, like we work a lot with SMEs. So none of the products that we built in Elsevier will be released without like going through an SME pass. So everything that we do would be curated by SMEs because it is like affecting the customers or patients at the point of care. So if we build something automatically and if that turns out to be like a wrong decision by us, then it might result in an adverse impact basically. So everything that we build will go through a manual SME scan to certify that the content is like authentic and it could be released out. So we work a lot with SMEs, wherein we try to understand, like say, what are the rules that needs to be used for actually applying either NLP or deep learning techniques on these kind of documents to identify the relevant content, and basically build models or create rules to extract the content. So once it is done, then we basically like do a gap analysis to figure out like whether the content is already existing in the taxonomy or not. If it is already existing, we'll exclude it. And the ones that are not part of the existing taxonomy would be sent to the SME for curation. If it is like a non-English language, then also we do a translation to English to do a gap analysis to figure out like what's the coverage in English and what's not part of like the existing coverage. And if it is already part of English but not present in the non-English language, then we know that these are the terms which are already validated. Either we can translate them directly or ask SMEs to do a manual translation. So there is a back and forth machine translation that is employed here to convert like non-English to English, do a mapping and English to non-English. And that would be curated and added back to the taxonomy. Yeah, we have an internal NER system which tries to tag like concepts which are part of the ontology that we built. Again, we are not identifying like any term or any n-gram that is present in the document, which is could be a like valid noun chunk. Okay, because our focus is to extract only those content that is relevant to a medical terminology. So we don't index anything that is not part of an existing medical terminology. So everything indexed is a medical term basically. So we have internal NERs which can tag like these medical concepts that are present in the ontology in all the languages that we work with. So this will also identify all the synonyms, and they have like ways to normalize the text and try to identify whether like a slightly varied form of a particular concept is actually the concept that we are looking at or not. Yeah. Oh, by this, like say we standardize like the concept tagging mechanism so that like everything that we tag is actually mapped to a standard IMUI, which is a unique ID that helps us to quickly identify relevant content. It also helps in better discoverability, and we can do a better indexing with this. And as I've told you, like, say we have different offerings. So if you have content in English and if that book is like valid even in like non-English countries like probably Germany or Spain. So if you want to use the same content because it's already indexed in English, so if somebody searches for a term and if that term is already existing in like Spanish in our taxonomy, you can quickly refer back to the English indexed content and do a machine translation and show it to the end users. So for building like these searching, I mean say the corpus, entire corpus is tagged so that it could be indexed in the subsequent steps. So the other important part is like relation extraction, because in previous queries we have seen what are the best treatment modalities for treating breast cancer. So we need to know, like say there is the user is looking for like a particular disease and a symptom or a drug or a treatment modality for it. So we need to identify what are the various concepts that are there in the search query and figure out, like say, what relations exist between these two concepts. So we do a lot of relation extraction. So a relation triple basically has a subject, a relation type, and an object. So example here is like asthma has drug albuterol. So by this we know that like if somebody is searching for albuterol, we can retrieve all relevant documents where albuterol is mentioned, and also like say it has a relation with a particular disease. So for this, like we employ a set of deep learning techniques to do relation extraction from unstructured content, wherein like say, as I told you, like it goes through a manual process. So we basically assign a default rank saying like this, the machine learning algorithm is confident about some percentage about the extracted relations, and it has to go through a manual pass. And there are also like a rule-based techniques. So these are predominantly applied on structured documents because the document is well structured. We precisely know where exactly in the document a medical term would be found. And if we are able to extract, like say, relations from these kind of structured documents, then we can, with very high confidence, say that this is actually a valid relation and could be used directly because the structure is well placed. I mean, so document is well structured. And most of these relations go through a manual curation, and they are ranked based upon like how common this relation is, how rare it is, okay, how frequently it is seen, so on. And we have different categories, and based on those categories, every relation is ranked. For example, there is a rare disease which we have like found a relation between like different medical terminologies for the rare disease. Then we rank that relation very high. If somebody is searching for that rare condition, probably the document which has this rare disease combination would be popped up as the most relevant top result, basically. And we use this relation extracted information to build the ontologies and build indexes and retrieve the content. Yeah, this is one graphical view of like how the information is captured within the knowledge graph. So here you have like a document which talks about asthma. Basically, I've taken a screenshot or a snapshot of clinical overview, wherein it's a structured document, and you're seeing like a part of the document which talks about the key points. Okay, here you see like there is a because this document talks about asthma, so we know that this is the concept asthma, and this is the unique ID 2800541, and asthma has document a specific document, and we have like the ID or unique ID of the document which says that this medical concept is mentioned in so and so documents. If you want to go back and identify what's the source from where we have extracted this information, we have that recorded in the knowledge graph. And there is like a slight variant of asthma, which is like cough variant asthma. And you see here the relation type is has related document. It's not exactly the document, but it's a related document. It's a slight variation of the original term. And asthma has a clinical finding cough. Okay, the relation between these two terms is clinical finding, and the source from where we extracted this relation is that particular document. So everything is, as I've told you, it's evidence based. So if somebody would like to know from where we gathered this information, we precisely can pinpoint, saying like this is the document from where we extracted this information from. Yeah, let's look at like the indexing process. Again, like this is a very high level, so I'm not going to go in detail about like what exactly we do within Elsevier. Just to give you an overview of like what's the process. So we have like input documents. We looked at like the various type of documents that we use as part of the corpus for building these, building the search engine. So every document has its own format and own structure. So we gather all of those documents and we standardize basically the input format. So that like say we have like a common flow for the subsequent steps. Okay. So there are various algorithms and say depending upon the document, so we have different processes for standardizing them. So we standardize them and we put all of those documents into a common repository like S3 bucket or so, which would be crawled on a daily basis, and it will be indexed to build the, searches. So there are like a set of processes like named entity recognition, relation extraction, and few other processes which would be run on regular basis on the entire corpus that we have. And once these pipelines or processes extract and identify relevant content, we take that content and create a Solr document, which would be used for building a Solr index. Yeah. Again, this is like a very high level diagram which shows like when a user is searching for a query, how the content is retrieved and displayed to the user. So the user searches for a query, and that search query would be taken, and we run the query through a set of processes. Like one of them is query parsing, wherein we parse the query and identify what is there in the query. If required, we do a query completion, and we also identify what are the similar concepts related to the query and extract like all the results that actually meet these criteria, and have like a ranking mechanism to re-rank the documents and display the result back to the user. let's look into detail about like these 4 or 5 different processes that we have seen in the previous slide. The first one is like parsing the clinical query. Say a user is entering like a query like, say, what are the different differential diagnosis for treating asthma. So it has like various concepts. So in this particular, say, a screenshot, you see this is a query, asthma differential diagnosis. Okay, so we do like parse the query and identify what medical concepts are there in the query. So you see there is a concept called as asthma, and there is a relation type, which is like has differential diagnosis. Okay, and this is another example wherein we found like, say, there is a concept and a relation type, and this is like the third example wherein we found 2 different concepts. So basically this will tell us like what kind of information the user is looking at. So is he looking at only a particular medical concept, or he is trying to find out like, say, a relation between a medical concept and probably a treatment modality or diagnostic procedures or drugs, something like that. So that gives us like a particular semantic information, and we can focus our subsequent steps to retrieve like relevant content. So once we pass the query, then we try to complete the clinical query. So here you see like the original query is restless leg, and it's also a valid concept in our ontology. And you see like IMUI for that. And when we search for like the existing indexes to retrieve like relevant documents that have information about restless leg, in case like, say, there is no result that is available for this search term, then we try to transform the query. There are certain patterns which are like approved by clinicians internally, which says that if somebody is searching for a particular query, if you could not retrieve any result, then you should transform the query into different set of predefined patterns and search whether there is any content that is available for these kind of transformed patterns. Okay, the transformed pattern here is restless leg syndrome. We see like whether there is a content available, and it's also a valid emmet concept. So if there is any content available, then we pull that content and display it back to the user, saying like, you search for restless leg, but we found like content for this, which is like restless leg syndrome, and you see, you decide whether it's relevant or not. And there is another example, obesity hyperventilation. Here actually it's 2 different concepts, and we have a transform query in case like, say, we don't find any relevant results. And here basically, since these are 2 different concepts, displaying results for obesity and the other concept might not make a lot of sense, because the user is searching for like, say, a phrase. If there is any content that actually captures document containing this phrase, that would make more relevance. Okay. So in these kind of scenarios also, we try to see if we can transform the query and check whether there is any relevant content for these transform queries. If it is there, we'll display it, and we'll also keep a track whether these kind of transform queries already exist in our taxonomy. If they are not, then we'll have like a separate gap list that would be sent back to the SMEs, and they will validate whether it's a valid term or not. If it is a valid term, medical term, then that would be added back to the taxonomy. Yeah. And one other thing, like, say, we have like autocomplete functionality, as you see here. When somebody is typing for asthma and D, he gets a list of all options for which we have like content indexed, and these are valid emmet concepts. This is to ensure that, like, say, the clinicians don't type in wrong the search queries with spell mistakes and all those things, and they end up like researching the site for getting like relevant content. Yeah, and the third one is like seeking similar concepts. So here I have given like 3 different examples, like ABCD2 scores. Actually, this is a score which will assess the risk factor for a particular disease, like so if a user is actually searching for this score, and if there is no content for this score, or if there is a content but 1 or 2 documents which actually talk about this score, but few other documents, many more documents that actually talk about a disease for which this score is like being used to assess the criticality of the patient, then we also surface all those documents which talk about the disease. Then the second one is Quercelia. Like, this is actually a bacteria, and somebody who is searching for this bacteria would also like to know about like what diseases would be um, occurring as a result of having this bacteria. Okay. And the third one is again like a medical examination test for a particular disease. So we try to have like similar, not only looking at synonyms, but we also try to see like what relations exist between different concepts and try to extract all those documents. And once like the primary concept, the secondary concept, and the relation types, everything is extracted, and the query is sent for like retrieving the search results. Once we have the results, we have like a base core calculation mechanism, which will take into account a lot of boosting factors, because not every document is highly relevant for a medical practitioner. There are certain books which are very authentic, and the information that is available there should be like ranked very high. So we take into different parameters. So one of them is like content type boosting. Like we have clinical overviews, books, journal articles, clinical calculators, clinical trials. So depending upon the query or the term the clinician or the point of care person is searching for, if you know that like these terms are pretty much valid for, I mean say there are certain content types that are valid in these kind of search scenarios, then we try to boost those content types. And impact factor. So if you are extracting like say journal content, then we take into the impact factor, like how impactful is the author and how many people are citing this particular journal article. So that actually impacts the search results. And there are some manual boost factors for certain books, like Ferris, for example. That's very popular book, and most doctors or medical students use that as a standard Bible for their education. So any content that is retrieved from Ferris would be boosted very high. There is also like dog boost date. So based upon the recent publication date, some might be like if it is published like 5 years or 10 years back, there could be a scenario that it might have like a lot of revisions and the data that is published like back date is outdated. So we try to give preference to the latest publications again. Yeah. So this is how basically like we extract the content, rank the results, and display it back to the user. Okay. So I'm not going into the details of like what's the accuracy, how do we measure the uh, relevance and all those things. But I'll quickly cover like say one area where we try to identify the results that are retrieved and how we incorporate that feedback back into the system to improve the quality of the search. So we have a mechanism internally to keep track of all the searches that the users are making. And we don't actually capture like personal information saying like person ABC has did this search. So it's at a very high level, organization level. If you have an account, at an account level, we know what kind of searches are made by the users. And we use that information to analyze like say what results are being surfaced back to the user and which particular result he clicking, to identify or to get a feel of like whether the results that we are surfacing are relevant to the user or not. So there are different type of, I mean, say content that is recorded in the session logs. So one of them is like view content. So basically, this particular piece, the view content piece, comes as part of the redirection from other sites. So there could be like a link which a university professor might be giving to a student, saying like you go to this book and study. So they simply click on the link. They are not making any search basically. So it's a view content. So there is nothing we can track. It's a direct link to the book content or any specific content in the website. And there is like type 2, which is like a user is searching for a query and he sees a set of results. He clicks on one particular result and that's what is the result that he wants, and he is not doing any other activity. He reads through the document and he basically disconnects from the session. Again, here there is not a lot for us to do. And this is like type 3, wherein a user is searching for a query. He gets a set of results. Then he basically clicks on a particular result. He is not satisfied. And again, he searches for a different query or the same query. He gets to see a different, I mean, it's the same set of results again, and he clicks on some other document. Basically, he is not satisfied with the first click that he has made. So he is researching again, like searching till he finds a relevant document. So this is like a set of data that we are pretty much interested in, trying to understand like whether the results that we are displaying are relevant or not from the perspective of the user. So we call these as informational search queries. and we do a lot of analysis. Here is one example, like the user has searched for Fowler syndrome, and he ends up seeing a set of results, and these are like the set of three results that the user has clicked on. So these are all coming from a particular book. This is a book, and the user is looking at different sections or chapters within the same book to get information about this particular search query. And as you see here, the first result that the user has clicked is not part of the top 20 queries that we have, top 20 results that we have displayed to the user. Okay, that's the reason you see a -1 saying like he clicked on some result which is in second or third page, probably. And this one is a result that was clicked by the user, and it is 18th in the position in the list of results that we have displayed. And the third result that the user clicked on is actually the second document that we have surfaced. So this will give like us a sense of feeling like what the user is trying to search and whether he is able to get like the relevant content. Sometimes what happens is like if the user is a student, medical student, he is not sure about like whether he should go and click on the first book or not, because somebody told him like find this content in so and so book. So he is particular about like looking for a book which he knows about. Okay, he goes to like second, third, fourth page, tries to see like if he finds that book, and he clicks it. So we are trying to understand like the pattern of searches at a different user level, whether he is a student or a researcher or a clinician or a nurse, and based upon like the pattern of searches and the results he or she is clicking on, so we get a feel of what kind of data a particular user is looking at, and based on that we can reformulate our search logic and probably index it in a more relevant fashion. Yeah, that's all. Do you have any questions for me?